Next-Gen Pledge focuses on acute and chronic cardiorespiratory illnesses that accounts for 34% of acute hospital admissions worldwide and are a major burden for hospital admissions. Next-Gen Pledge, standing for Next Generation Personalized Edge AI in Healthcare, offers a solution that encompasses TERMINET's framework for testing, validating, and demonstrating federated models and machine learning algorithms in a personalized healthcare scenario. Our efforts focused on the provision of transmitting medical data to the back-end TERMINET infrastructure, and on the provision of prototype services capable of performing Edge AI in a single system, enabling medical knowledge creation and exchange. The main components of our solution consist of two wearable devices, patch and wrist form factors, allowing for testing a plurality of different embodiments and implementation interfaces, as well as a clinical decision support system, noted as CDSS, that will undertake the processing of incoming raw data, and will also act as the interface to the TERMINET federated learning pipeline. The main components are the following. 1. Tau-Hetric Beat wearable patch sensor and edge platform for biosignal capture and analysis. 2. The clinical decision support system, which enables real-time recording of vital signs, such as blood oxygen saturation, respiration, heart rate, and body temperature, utilizing the advantages of edge computing, ensuring data privacy and security, while minimizing latency. 3. A third-party wearable IoT wrist sensor, which offers data for the assessment of heart rate, respiratory rate, blood oxygen saturation, and body temperature. More specifically, TrackBeat has developed and patented a novel wearable sensor and algorithms capable of capturing photoplethysmography at multiple wavelengths, as well as ECG at high sampling rates. In conjunction with an embedded accelerometer for activity measurement and a skin temperature sensor, a complete personalized image of a person's physiological and behavioral status is captured. The associated algorithm processes all incoming data streams to train a personalized model for the assessment of heart and respiratory disease-related factors. The clinical decision support system enables real-time recording of vital signs, such as blood oxygen saturation, respiration, heart rate, and body temperature. It utilizes the advantages of edge computing, ensuring data privacy and security, while minimizing latency. The third-party wearable IoT wrist sensors offer data for the assessment of heart rate, respiratory rate, blood oxygen saturation, and body temperature. Our sensor can be used in two different ways. Either at wrist, for long-term monitoring on the move, or at chest, as a short-term, overnight, highly accurate monitoring patch. It offers 24 hours continuous and synchronous monitoring of 9 biomarkers including electrocardiogram, blood pressure, heart rate variability, respiration rate, oxygen saturation, temperature, and activity recognition. It can be reused and be sterilized. Next-Gen Pledge leverages TERMINET's architecture in a scenario incorporating AI edge methods and algorithms for a real-life clinical application, interacting with already defined TERMINET centralized federated learning for training and inference. We focus on overcoming the barrier of secure sharing of medical data on cloud infrastructures to retrain models at the edge to create both technical and business advantage. That is the reason that we interact with the already defined and implemented centralized federated learning system developed for the TERMINET project consisting of two separate phases, the A, federated training, and the B, inference. The federated training procedure within TERMINET is an offline process. The process follows the described centralized federated learning pipeline. The federated server is a component that resides in the platform layer of the TERMINET architecture and is in charge of orchestrating the federated procedure and operations, query the remodel federated clients, retrieves, aggregates, and redistributes the federated models. To assess the impact of federated learning, two data splitting scenarios were analyzed. First, a balanced split was performed, representing model sharing between two equal-sized, Party 1 and 2, hospitals. The dataset was randomly split into two subsets of the same size, one for each party. Second, an uneven split was performed, representing federated learning between a large, Party 1, and a small, Party 2, hospital. From each subset 80% was used for training and 20% for testing. When testing, a concatenated test set from both parties was used. This allowed for an objective evaluation with a larger testing set that is not known to neither Party 1 nor Party 2. To study the impact of vital signs, as a source from the wearable devices, on the hospitalization prediction, two versions of the dataset were used in all scenarios, one with all features, and one with all but the vital sign features. In this slide, we present the accuracy results for the system, for the case of balanced split of the dataset, before and after federation learning through TERMINET, with and without vital signs included. In this slide, we present the accuracy results for the system, for the case of uneven split of the dataset, before and after federation learning through TERMINET, with and without vital signs included. Overall, we managed to increase CDSS accuracy by 21% when using the federation scheme provided by TERMINET. By introducing vital signs in the federated learning scenario, we achieved a further increase of 7% over the classification scores without vitals. In summary, we met all project's objectives with a CDSS accuracy greater than 20%, outreaching our initial target by a factor of 4. Next pledge, as well as the provided devices, were successfully integrated with the TERMINET framework, the federated learning modules and related subsystems. Next pledge visibility and outreach was achieved by participating in one workshop, one public event, and an international exhibition.